Very good afternoon to all. This is the final part on the neural network theory and application, and this one is one of the final ones on the applications that we show using neural network, mainly neural network, and some of its hybrid system based on my general publications that we've done within the last 15 years or so. We have many different publications, many publications. These are some of the few basic ones that I'm going to show. Some highlights of the application that we have used for this neural AI, and simulation, and some online application basically based on the the first one is on a paper we published quite some time ago. This is on the simulation and experimental implementation of a neural network based internal model control strategy, and this is on a reactor system. Okay, it was published some time ago, 2007, and chemical engineering communication, using an inverse model based control strategy for nonlinear systems, and we have used it to control the partially simulated pilot plant vector, mainly the temperature, which this system exhibits steady state pneumatic stability and also nonlinear system. So we use it for set point and plant modification. And this is an actual pilot plant basically in the lab, and it's really a very important breakthrough in the use of neural network for real systems that test for set point and also disturbance rejection. Okay, and it's able to demonstrate the capability of applying neural network based control system in real system. That's the best. The real test is in the. So this is basically the PASEC plant, a simulated reactor, where you don't have real reaction, but real reaction is being simulated by equation. You simulate the equation basically by adding in the basically we have steam coming in that will simulate the exothermic reaction. We calculate the exothermic reaction, how much heat coming in, so that's being implemented online through the amount of steam that will give the amount of heat based on whatever simulated reaction that you've got. And then we do the cooling outside. It's outside cooling, cooler system, so to control the temperature inside the system. So we call it a partial simulated vector system. I said this is a real one, a pilot plant simulation, not too an issue, but the real world where instead of having the jacket, we cool it through external cooling. Okay, and this is the plant in the system, and we use the IMC, as we mentioned before in my previous class, using the neural network model and the neural network inverse model as the controller with the filter to accommodate different strategies that you would like to implement in the system. And as the same as before, we put the pass output, pass inputs, and set point into the neural inverse model to get the manipulated variable to come out with the output that is close to the set point. Of course, to cater for disturbances and mismatch, so we have another neural network fault more in parallel, and this error will come in subtracted from set point to the filter and to run the system. So we have many different results. Some of the basic results that we're using a set point tracking. So we see that the temperature is being tracked a bit slowly, but still going towards the set point. Okay, by just a neural network system. This is being trained offline, but then implemented online without any adaptation. So it's still very good set point tracking. And this is the manipulated variable. Manipulated basically is the basically will be the set point of the cooling water. So whatever cooling water set point is needed to make it whatever you want is being tracked to the neural network, manipulated following whatever is supposed to be, and very closely here. Here's a slight offset which can be reduced to a little more adaptation. Using IMC, we may have some slight offset, but that can be reduced to adaptation of the neural network online. Inverse model can be adapted online. Okay. So, and that's for set point, the servo tracking system. And for disturbance, we disturb the system We can disturb in many ways, changing the feed flow to the system and so on. Feed flow and so on. It disturbs, it goes either high or low. In this case, it goes high up. Okay, we heat it up further, it goes high up. So implement the neural network, bring it back to its set point. Okay, just to go to the TJ set, as I said, is the manipulated variable, the actual neural network following that and giving a slight offset, which, as I said before, can be adapted for this. So this is a real application of network, shows that it is slightly verbose. It's not fully verbose yet. We have not tested, but at least it can do some servo and disturbance tracking in the real world, and which means it can be used in the real world for many control system strategies that we normally find. This is a typical reactor system, and neural network has shown its capability to be able to track nonlinear system and control nonlinear system as we would normally do using other control methods. Okay, another one is published in 2006 in the Institute of Chemical Engineers transaction ICHEME on neural network-based modeling and control in a batch reactor. It's another typical nonlinear system, very highly complicated, difficult to track. So we're using a neural network system to do the control in this case, and basically in relationship with a so this is the batch reactor system as normal, heat or cool depending on what sort of batch profile you wanted to get. Okay, we again use the inverse model temporal strategy, the neural network inverse model and the neural forward model with the plant in parallel, pass input, pass output, and also we use a neural network estimator to estimate the heat release. The heat release is something that's not easy to calculate. You can measure. So in this batch exothermic reactor, we need to get the heat release. Changing is not constant. It's changing in the batch system. It's not easy. We use a like estimator. It's like a forward model method to be able to also predict the heat release and implement into the optimization system. Okay, the optimization system. But in this case, we basically using the neural network inverse as the controller itself. Sometimes we use it within the optimization system. This one we use it as a controller itself to be able to estimate the neural network, the heat release, which is also part of the input going into the forward model. The heat release being used within the forward model and the inverse model. Okay, so here we'll see the different results here for set point. Okay, we have one set point tracking here, so it follows closely. Okay, and then we have different set points here. Slight, you cannot see the slight difference. For batch, normally we have different set points. Okay, here also you can't see the slight difference of set point, but it's tracking the set point nicely. Okay, for batch we don't have big variance, but there's slight changes in set point. So it's tracking the set point closely. And also this is for a model mismatch. When you have a heat transfer coefficient change, the thing goes out of control, but with the neural network system, it goes back, bring it back to the set point or set points that you would like it to control. Using this internal model control strategy system, I've said before, which is very dynamic, very nonlinear, very difficult to control using a PID system because of its nonlinearity. It's a lot of mismatch, a lot of it's difficult to predict. As I say, the heat release difficult to predict. Okay, the heat transfer coefficient change also difficult to estimate. A very highly nonlinear system. It's not fixed fixed set point. It's got a profile of set point. So all these things make it very highly difficult to control, which needs advanced control methods. We have other methods that are being used also, GMC and MCC and so on. But here we demonstrate the use of straightforward neural network system, which shows its possibility. Definitely can in this case, but only thing the range of temperature is not so high because that's what it is. But if for higher range, maybe you need to do some little bit changes in the adaptation of the inverse model and using adaptive or using hybrid system in for those sort of cases. So these are another example neural network in process system engineering research field that can be demonstrated for chemical process systems. Another one I've seen is using neural network for predictive control of steel pickling process. This is in 2009. This is in work with Chulalongkorn, Professor Pia Baisan, if you know, students, and also Dr. Wacheva from Burapha University, where she was my PhD student. And so this work was basically using neural network within the model predictive control strategy for steel pickling process, which is a real pickling process which has been a model. Not an easy system again, a very highly nonlinear system, a very tricky, complicated, complex system. So we use a multi-layer feedforward network within the model predictive system. Okay, and we use the ribbon market for the training of the neural network using normally MATLAB system, and it shows the feedforward neural network used to predict state web was over predicted horizon to obtain the optimal control actions. It's tested for set point tracking, disturbance, model mismatch, and this result shows that it shows better performance than the conventional and shows that it's very robust. It's a test of the robustity of the neural network, although it's in simulation, but the actual system has been modeled in simulation. So it's very close to the real world, and especially when we implemented it using having model mismatched and presence of noise, so it becomes very close to a real system. Or sometimes we can make it worse case than the real system itself. To be able to use online, we have to test the worst case in the simulation aspects. And again, okay, this is a steel pickling plant. Different tanks, we have different HCl concentration. Okay, we have to control the pH in each of them, and at the end of the day, we would like the concentration to be whatever that we have fixed for it. Okay, in the 15%, the final one, and the others as well. In this case, we implement on 15%. The neural network MPC. So the MPC optimizer we use model predictive control, but the model is based on neural network model. Right. So the same strategy as you said, but not as an inverse model as a controller, but as a model itself. Again, using the normal inputs, the various past inputs, past outputs, and so on. And the neural comes prediction with a range of output. As for model predictive, we need an output for future outputs as well. First, okay, the first prediction k plus 1, k plus 2, k plus 3, and so on for the optimizer to work. So he's using neural network as the future predictions, okay, and feeding it with the future for FI, the what you call basically the manipulated to the process. So whatever manipulated profile we want, the neural network will come out with the CI profile. It can be used in the optimizer and to come up with our control system. Okay, so this is the multi-variables, a lot of variables involved. Neural network model predictive control strategy. So we use it. He's just tested it for all basic set point, regulatory, and so on. Just show one result here for concentration change. It goes right into the concentration that we want from some other values. Okay, very closely controlled with very little disturbances, very little offsets, very fast control in the sort system. Okay, compared to the PI control, we can see the PI control overshoots, takes some time to reach, and things like that. Okay, this is just one example. Even other result neural network show much better more strategy, and this is an advantage over the conventional PI control, as we mentioned in my first class. That advanced control like AI control, neural network control, be more tight control. Doesn't have too much variation, overshoot, very tight to the set point, little variations, little changes, and more quite often faster to reach to the set point, which is much needed in this sort of system, which we want to control it quickly, fast, but at the same time tight control, which not much variations, because that can spoil the whole system if we have too much variation within the concentration. So this is where advanced control It's a must for this sort of system, and neural network AI controllers have shown the capabilities in this sort of things. Is using this is what 2006, all this quite some time ago. We have a recent one, but it's like some time ago. We have been using all this for quite some time. Study of neural network based controller for controlling dissolved oxygen concentration in a sequencing batch reactor. We call it SBR. Here we use the neural network and direct inverse IMC and hybrid neural network to maintain the dissolved oxygen in the activated sludge system by manipulating the airflow rate. Okay, so it depends. The controller depends on the neural inverse model and the forward and the inverse model. Okay, we also have the hybrid neural network in parallel with the PI controller. So the different sorts of strategies we use for multiple set point, disturbance, noise, and so on. So you can go into this paper later and see the detail, but it's just to highlight some of the main things of our work and the results in our work that will be useful for you to see how neural network can be used in different different control strategies, different systems, different sets of performance criteria. And again, you can see that the this is the system SBR. Okay, we are manipulating the airflow rate to control the DO, dissolved oxygen, within the SBR itself. Okay, also very highly nonlinear system when you model it. Very complex system because it involves biological system. It involves what do you call all these biological balances. It involves not only the normal input output, you should have all these systems of that biological system that decompose and so on. So there's a lot of involvement. It's not just straightforward reaction, but a lot of non-linear system with that. A lot of equations involved. Okay, so not simple just using a PI and so on because of the complexity. So we use a neural network inverse. But this is a straight direct inverse model. One of the control strategies that we've taught you in our class, direct inverse model to control the SBR, which is quite a good method. Using again the inputs, the past inputs, that one minus is a past input, the past outputs, and of course the set point. Straightforward to manipulate the dissolved air coming in, to manipulate the DO of the process. Straightforward neural network control system. So it's mentioned just now, tested for different set points and different also disturbance and noise to make it robust. We have to not only set point, as I said before, to have disturbance, and we also use other change of model mismatch, noise to make sure that systems is robust. In this case, first of all, we use a multiple set point for the DO, and you can see the response follow from basically no action at all, doesn't know where to go, start from zero. Not normally happen, normally it's close, but it's just to see whether it can follow or not. Follows through very nicely the set point in this multiple set point tracking strategy. For one, if you can do it multiple, definitely for one set point, it can do much better. So that's a basic test for servo control. So we have disturbance, we don't show it here. And then here we have with disturbance, we have disturbance as well, and measurement noise. Some disturbance coming in, it reject, and also putting noise into the system to make it look real. Real world will have noise coming from the actual measurements and so on of the DO. So we'll have noise coming in. So it's a real noise, but it still can control. With the noise, doesn't affect the structure of the neural network, the prediction of the network, the stability of the neural network, robustness of the neural network, which is a very highly important part of control, but it still can control with that noise, doesn't matter. But within the set point, it is still controlling the system as per the requirement, as per the criteria that is required from it in this sort of system. Right? So this again shows the robustness of implementing neural network control strategies in process system engineering, mainly chemical process system, in another system, very typical in the real world, the SBR, sequencing batch reactor system. Okay, there are many reactors. Is one of them. It works for one. It can work for the others as well. So another one. Finally, we have the one we use. We just published 2011 control engineering practice. My student on control control of polystyrene batch reactor using neural network based model predictive control. Again, it's another system where we use neural network model within the predictive control method, and this is another experiment. This is experimental investigation. This is also another real world application to test its application in the real world. Okay, controlling batch polymerizers, of course, you know it's very complex, not easy. Okay, model predictive control has become a leading technology, but again, difficult to get models. The model predictive control need models, and you need to get good models. Not easy to get because of that. So in this case, we use a neural network, and so what we do is in this neural network model predictive control is implemented to control the temperature of the polystyrene batch reactor, and the controller set point and load agent performance are investigated for support and for regulatory control. So in this approach, the neural network model is trained to predict the future process response over the specified horizon. Okay, and results are compared conventional PID again to show its superiority over the conventional system that is good for linear system but not for non-linear, and it's superior to the conventional, especially during process startup. This process startup is where it's become the most difficult part of the controller because it's very highly unstable. Yeah, it's very what you can say is basically batch in nature, the startup. But this is where we need to have a control to make sure that it's smooth and also less variability. We mentioned that it's important part of advanced control, and this result shows what we have already said about the advantage of advanced control methods, the modern advanced control methods over the conventional PID. And again, this is a system, the real world system. We have all the different components. Okay, but at the end of the day, it's a polymerization system, polystyrene system that we want to produce. Okay, and control the temperature. The temperature very highly important profile that we need to follow. We cannot go too high away from the profile because it will spoil the polystyrene polymer reactors, batch reactors sort of thing, and like penicillin and all these things. We need very tight control. Anything too high, it will spoil the polymer, spoil the fermentation system, or spoil the penicillin system. So we need very tight control, and this is normally given by advanced control methods, typically like AI control and neural network control. So in this case, we are having the neural network model within, again, the MPC using a model within an optimizer, right? And the plant data that we feed into the neural network, we don't show everything, but again, normally when you talk about dynamic neural network, we need the past values of the inputs, outputs. It's not static, it's a dynamic system changing with time. So we need to have the different input output structure into the neural network and model. So you fed it into the neural network model, it gives it the model will feed back into the optimizer. Optimizer uses the model to come up with the use that will be used to control the system, with the many use for the future, but normally we implement the first one, then we go again to get the next one and implement the first one. So it's just optimizer. Normally we give a profile called horizon of values, but the implementation is normally one. We call it the residing horizon control method. Okay, but the optimum is normally with profile because that gives a better result when we have a future profile than just one profile. But the implementation normally is, of course, the next one. Then it goes again. So a recurring, but implement one, a recurring and implemented one. Okay. So this neural network based model predictive control base, we use it to have this profile with noise, of course. Noise, because real world is noisy. The temperatures not coming just steady like that. It's going to be a little bit noisy due to sensor measurement, sensor noise, in the sensor system noise, and so on. Many effects of noise, which are real world. But the neural will be able to track it nicely within its profile. Okay, this has been trained offline. It's not online. It's been trained offline, implemented online with noise, but it's still able to track nicely the profile using neural network model predictive method. Okay, and okay, we have this. Not shown here, but we have some disturbance. You can still bring it back. Uh, Even under disturbance, it will be bring it back to the profile that we are using it. And also, finally, it's able to compare the advantage of this. Normally, people will say, okay, why don't you PID? Okay, we use PID, but use PID, there's an overshoot. Initially, later, you pick it up, but this overshoot may not be acceptable in some system. It may already spoil the polystyrene, may even spoil the product that you have. If it's too high temperature or too low temperature, whatever, so the image already spoiled. So that's not acceptable in many cases. Even if you have disturbance, also same thing, it may go out of range. This is again the advantage of advanced control, give tight control compared to PID. It may work at the end, but at some point it may just overshoot over the boundaries that will make it totally unfeasible, not acceptable. You may have to close down the system and do it again and so on. So it's a lot of waste, a lot of time wasted. It's not optimal. It's a lot of energy wasted, and also it's not an optimal method in this sort of case. So it's not just looking at the end, it works, following thing, but you have to look at certain points. Where a model mismatch, we have disturbance, PID may go out totally, but neural network will be able to control because of its nature, its robustness. You have not one input but many inputs coming in, the past inputs, past outputs, and so on, that makes it more robust, more stable and more tight. And so if you have, again, follow the steps of the modeling using the right data, good data, enough data, good input output pattern, good neural network structure, the right activation function, a lot of testing, training before you, and validate before you implement. It's not just straightforward. You have to do all this, get it right, then implement it. Again, this is implemented online, but it's trained offline. You can do it, as I said, again, adaptive, but since we don't need adaptive, we don't have to. It doesn't follow for closely. We can do an adaptation online, slight adaptation online, and then let it track again, which can also work. In some cases, we have shown it work. I didn't show here, but in our work that we've done for the real Percept, we do a adaptive neural network controller. Also, we have an adaptive fuzzy logic controller to implement into our system that will cater for slight disturbance, model mismatch, or whatever in the real world. So that can be done. It's not something difficult. It can be done. Only thing, we'll have to make sure that the adaptation can be done quite fast. Adaptation, not every step. Maybe after a few cycles, we adapt and change the neural network structure. In terms of what is the structure, the nodes, mainly the nodes or the weights within this. Normally, maybe structure we don't change so much. We just retrain it to get new weights to adapt for the different data set coming in. The data online is another data. Previous one we train in offline data, but data that is coming online with new data, that's new data. So being trained with previous offline data, a new data set that will be make it more strong. As I said, the strength of neural network AI, especially neural network, is basically on the data set. The more data set you have, the more variable data set, the bigger range of data set you get, the more robust, the more accurate, okay, the more strong the neural network optimization will be. And that's what we have. So we have extra data, we feed it in, but again, you don't change it every time. After certain data set, you retrain the network, which is not so much different from the nominal point. The normal points, when you have coming implement online, they may be slightly different. That is good enough. But if there's a major difference, then that's a big issue. Means the nominal has already changed, the nominal operation changed, the nominal characteristics changed, then it may be difficult for the network. That one you may have to retrain again offline and put it back. But if it's within close to the actual nominal training, it's okay to add more data and train the neural network. It's possible. It's not something difficult for AI sort system. This is why we call AI artificial intelligence. It's got an intelligence as long as the training data is good within the operating range and not too far different from what it has been trained before. Okay, so these are some examples of AI systems used in process system control strategies. you can see how useful this AI methods. If you can improve it further using hybrid models with first principle system or with neural fuzzy and all that, you will get improvement and improvement. This is going to be the future work using AI system. Thank you very much for your time. That's all for our application in this final class for AI.